All right, so carrying on here. Now, still have Earth here, but now we're actually twice as far above the Earth as we were before. So before we were just 1 Earth radius above the Earth's surface, but now we're going to be 2 Earth's radius above the Earth's surface. So center of the Earth here, 1 Earth radius, another Earth radius, and then 1 more. And now we're in orbit around the Earth, 3 Earth's radius from the center of the Earth. So now this is 3 ER, or RE. So again, calculating the gravitational force here, we would have G M1 times M2 over, now 3 Earth's radius is our separation distance, and squaring that. When we expand this exponent, we end up with G M1 M2 over 9RE squared. So now we see there's this factor of 1/9. So that's going to be just 1/9 of our initial gravitational force 1, which was back when we calculated the gravitational force just on Earth's surface. So we just have to do 1/9 of the 490.67 newtons, and that will give us our gravitational force when we're now 3 Earth's radius away from the center of the Earth. So 1/9 times 490.67. So now the gravitational force is 54.52 newtons based on my calculation. And we'll just keep going for 1 more. We've got Earth again, center of Earth. Now this is adding a whole nother Earth's radius. So this one was R equals 3 Earth's radius, and this one is R equals 4 Earth's radius. So we have 1, 2, 3, and 4. Our denominator is 4 Earth's radius squared, and we're going to operate that square, and we're going to end up with 1/16 of the initial FG1. So 1/16 of that 490.67 newtons is 30.67 newtons. All right, so we kind of get this. We get the pattern. The reason I did this is I just want to reiterate what this graph is going to look like for a gravitational force, Fg, versus the radius here. I'm going to take a second to think through how to scale this graph based on my numbers, and then we'll come back and we'll show what the plot looks like. All right, so now I'm going to plot all my data. Oh, and I screwed up my scale because this actually isn't 19, it is that plus 6. So I need to redo my scale real quick. All right, trying again here. That point does not count. So this graph looks like this, which if we zoomed out, if we really were graphing this and we were able to look at it, looking at Fg versus R, right, this is going to be one of those rational functions. Where as R gets really small, that gravitational force gets moves towards infinity, and as R gets really large, that gravitational force approaches 0. I know you all studied rational functions back in Algebra 2, so I just love bringing this up, those limits as, you know, the function approaches 0, as R approaches 0, the function approaches infinity, and as R approaches infinity, the function approaches 0. So really seeing that as a pattern in the universe, that this function has real meaning for us. So this gravitational force is really related to Coulomb's law, just like I've said before. So the gravitational force is an inverse square law. This is just a pattern in nature that comes up. So let me just remind you what the electric force looked like. So Fe was that Coulomb's constant times Q1, the charge of the first object, times the charge of the second object, divided by r squared. So this looks very similar to our universal law of gravitation, different constant, and we're dealing with the attraction of masses here, but it's all over this separation distance squared. So just one of those kind of beautiful symmetries of the universe here. All right, so what we're going to do next is just apply this function. Later in either a reading or a lecture, I'm going to actually give you some history on how did we figure out what this gravitational constant is, this g, 6.67 times 10 to the negative 11th. There was a very sensitive experiment that a scientist named Cavendish did, and I don't remember the date. But he actually, did a very sensitive experiment with small masses and was able to quantify this force down to that 6.67 value for the gravitational constant here. And then later we've kind of replicated that experiment with increased sensitivity, and our value has gotten even more accurate, but it's pretty close to that still. So for right now, we're just going to accept that that is the value, and then we will apply this to some problems here. All right, so first practice problem. We are going to use the universal law of gravitation to actually calculate the mass of the Earth. So this is how we know the mass of the Earth, or one way that we do. Independently of the universal law of gravitation, we can go to the North Pole, stand on its surface, and do some experiments where we drop an object and measure its acceleration as it falls towards Earth. So independently, you can go measure that an object will accelerate towards Earth at a rate of 9.83 meters per second every second. And through the geometry, again, independently, we know that the radius of the Earth at this point is 6,371 kilometers. That's our distance here. We are dropping something that has a mass of m. I'm going to call that m1 is just some unknown mass. m2 is the mass of the Earth. That's what we want to figure out. And we have measured the acceleration. All right, well, how are we going to get the mass of the Earth out of this? Well, first, we always start with a free body diagram. So, if we're looking really closely, here's that object. And as it's accelerating towards Earth, you've let go of it. So the only force acting on it is this gravitational force Fg. So F net is just Fg. And then we also know that acceleration comes from having a net force acting on an object and then dividing by the inertia of that object or its mass, so how much it resists accelerating. Okay, so we know the acceleration. We know that F net is just this gravitational force, and then we are going to divide that by the mass. So let me plug in this value for the acceleration. You've got 9.83 meters per second every second. F net is Fg, and then we're going to divide by, let me add a little subscript here because that is the mass of object 1, or the mass of, let's say it was an apple, Ma. So I'm going to put the full expression in for Fg here. So this is using the equation for the universal law of gravitation. And then all of that is Fg, so that's being divided by Ma. One of the interesting things here, mass doesn't matter, right? All objects have the same acceleration towards Earth. The mass cancels out of this, right? It's independent. The acceleration is independent of the mass of the object that we were dropping, which is why we didn't need it. So since those cancel, they're both, one's in the numerator, one's in the denominator. This reduces to 9.83 meters per second squared is equal to g times the mass of the Earth divided by the radius of the Earth squared. I'll add an RE here. Okay, well, G we figured out from our Cavendish experiment. Radius of the Earth we figured out through some geometry. So now we can actually calculate what is the mass of the Earth. And we could then go later and maybe check this by looking at the acceleration of the moon around the Earth or something else to verify that we still get the same mass of the Earth. So we'll just plug in those values. We have G is 6.67 times 10 to the negative 11th. Newtons times kilograms, no, mass meter squared divided by a kilogram squared. And then mass of the Earth is our unknown over the radius of the Earth, which we know is, we're in kilograms here, so let's do a quick conversion. Radius is 6,371 kilometers. I want to convert that into meters, so I know that there are 1,000 meters in 1 kilometer, so my units cancel. When I multiply these together, I get 6.371 times 10 to the 6th meters. So we have to put that in for R. And then square it. All right, well, from here, it's just values, and then we've got our variable here. So I'm going to put 6.67 times 10 to the negative 11th into the calculator, divide it by this value squared. And then using the parentheses as soon as I'm dividing here, closing the parentheses, raising to the power of 2. The units on this right now are going to be newtons per kilogram squared. So I'll add those in. Then I'm going to divide both sides by this big number. Cool. Put that into the calculator. I have to use parentheses because I'm dividing by something that has a multiplier to an exponent. So I have 5.983 times 10 to the 24th. Now let's look at units here a second for the mass of the Earth. We had to do a little side note. Meters over second squared divided by newtons over kilogram squared. We know that ultimately this should become kilograms, but let's see how that works out. Newton is kilograms times meters over second squared. That is the definition of a Newton, if we expand the scientific notation here. And then kilogram squared is still down here. So unit cancellation, I can cancel one of these kilograms squared with a kilogram, and then I can cancel a meter with a meter and a second squared with a second squared. So I end up with 1 over kilogram, which is like 1 divided by 1 kilogram, which is the same as multiplying up by kilograms. So it does become kilograms. Phew, glad that worked out. So there's our mass of the Earth. The Earth's mass is 5.98 times 10 to the 24th kilograms, which is one of the ways that we know the mass of the Earth, right? It's kind of hard to weigh something that we're all floating around in space on. Okay, let's try one more here to show you an example problem. Move this out of the way. All right, so it says use the law of universal gravitation to calculate the acceleration due to gravity on the surface of other celestial objects. So this is another useful tool that we can use the universal law of gravitation for. So what is the acceleration due to gravity on the surface of the moon? Well, there are a few things that we need to know for this, and this is why you will have these reference tables. So I will post this. First of all, let's pretend like we're doing our little experiment, and then we'll pull out the values that we need. So we're on the moon, and we're going to drop the ball. And the moment that I drop it, I see that it accelerates. So it's free body diagram. When it's on the moon, really the only significant force on it is the gravitational force. on that, I'm going to say on the ball by the moon, because now we're on the moon, we're not on the Earth. So this is a gravitational force between the ball and the moon there. Okay, so that means that our overall net force is just Fg on the ball by the moon, and that net force is going to cause an acceleration. Acceleration is equal to that net force divided by the mass of the ball. Okay, so since this is the only force, I'm going to substitute it into here. We have Fg on the ball by the moon divided by the mass of the ball will give us the acceleration. This is our unknown. We're trying to figure out what's the acceleration due to gravity on the moon. So we want to put in our equation for the universal law of gravitation here. So G, always the same value. We need the mass of the moon, the mass of the ball. You notice that I'm not consistent with where I plug things in here. It doesn't matter. That's a commutative property. So could be mass of ball here, mass of moon there. Then we're going to divide by the radius of the moon squared and divide by the mass of the ball. So just like before, right, this is in a denominator, this is in a numerator, so those can cancel out, which is nice. Doesn't matter what we're dropping. So we'll have that the acceleration is the universal gravitation constant times the mass of the moon divided by the radius of the moon squared. So one thing is we would need to know the mass of the moon to calculate the acceleration because we can't have two unknowns. So this is where we're going to just go to our reference table so that we can figure this out. Let's look at the reference table. So here is the data for all of the satellites. So we're looking at the Earth's moon here, and we can see that here's the mass and here's the radius, and that radius in kilometers. So I'm just going to copy those down. Okay, let's just convert this into meters real quick. So 1,737 kilometers. There are 1,000 meters in 1 kilometer. So I'm multiplying by 1,000 here. So the radius of the moon, it can also be written as 1.737 times 10 to the 6 meters. All right, I have all my values in the right unit. So now all I need to do is substitute. So gravitational constant, 6.67 times 10 to the negative 11th, newtons times meters squared over kilograms squared. Mass of the moon is 7.346 times 10 to the 22 kilograms, divided by our radius squared, so 1 point squared. All right, big calculation again. Careful with parentheses. Okay, divided by, add the parenthesis, 1.737 times 10 to the 6. Close the parentheses, square it. Acceleration due to gravity on the moon, 1.62 meters per second every second. Units wise, we can look at how that works out. We have 1 of the kilograms cancel here. The meter squared cancels there, and then we end up with, side note, newtons over kilograms. Remember that a newton is a kilogram times meters per second squared. So we're substituting that in for the newtons, so the kilograms canceled, and we're left with the units for acceleration. All right, there are some additional problems for you to practice that are posted on Schoology using just basically applying this equation. It's so useful and it's really interesting to figure out all of the quantities that we can calculate using just Newton's, well, really not Newton's, but the universal law of gravitation. So try those out and I'll post those solutions tomorrow. Thanks for watching.